Hi, everyone. Thank you for attending this talk. Today, I'll be presenting our work on massively parallel multi-version transaction processing. So nowadays, modern applications depend on high-performance transaction processing systems. And these systems process transactions such as consumer orders or financial transactions. And modern systems, they often use in-memory designs and multi-version concurrency control. They're using memory design because they provide the high throughput and scalability. And they use multi-versioning because it's ideal for content and read-heavy workloads. So multi-version concurrency control keeps multiple versions for each record. Unlike single-version concurrency control, where each transaction can only access the latest version of the record, multi-version systems allow transactions to access the current and the recent past versions. And the advantage of multi-version concurrency control is that it reduces the transaction conflicts. However, this comes at a high cost of overheads due to searching and allocation of versions. Here we show the TPCC benchmark of two systems, the OSDI and MSTO system. They are the successor of the silo database, and they represent the best known performance in single version and multi-version systems. In practice, multi-version systems show good performance under high contention. However, under low contention, the single version system shows twice the throughput than the multi-version system. To understand why multi-version systems have a high overhead, we show one example of multi-versioning in action. So in traditional multi-version systems, the transaction ordering is determined at transaction execution time, usually by assigning a timestamp. And the transaction writes allocate versions with their timestamp, as you can see here shown in red. They create versions based on the timestamp, and the versions are usually stored in a linked list. Here, transaction 1 and 3 write to the same record A, and their versions are stored in this linked list. Transaction reads need to search the versions based on the timestamp, and they usually search backwards from the most recent version until they find the version that's visible based on its timestamp. And our insight is that the allocation and search is performed during the transaction execution, which makes it hard to parallelize. And in this work, we propose EPIC, which introduces a novel GPU-accelerated multi-version concurrency control that ensures serializability. And it is the first multi-version system with good performance under all contention levels. Here we show the same TPCC benchmark with EPIC added in red. And as you can see, EPIC outperforms both OSDI and MSTO in all contention levels. What is EPIC's key technique? First, we process transactions in batches. This allows us to utilize the high parallelism and the memory bandwidth on modern GPUs. We choose to run transaction processing on the GPUs because nowadays GPUs can have very large device memory, over 100 gigabytes on the latest NVIDIA GPU, and we think they are ready for transaction processing workloads. Secondly, we allocate and search versions for the entire batch before transaction execution. And with the batching and the separation of allocation search from the execution, it allows us to efficiently parallelize these operations on the GPU. As a result, during transaction execution, no version allocation or version search is required. This greatly reduces the synchronization cost during execution. Here we show the architecture of EPIC. At the top, there are the incoming transactions, and EPIC batches the transactions into epochs. And for each epoch, it determines the transaction ordering beforehand at batching time on the CPU. And for each epoch, EPIC processes the transactions in two separate phases, the initialization phase and the execution phase on the GPU. During the initialization phase, Epic allocates versions based on the right set of transactions. Here, for example, transaction 1 writes to row 3. Epic would allocate one version on row 3 for that transaction. And Epic also uses the read-write set of transactions to determine the version numbers for each read and write operation. Here, as shown in the execution plan, the transaction 1 reads from 2 rows, row 1 and row 2, and the corresponding version is searched or is located during the initialization phase, V1 and V2. And the version allocated for the write to R3 is also located for the write. Given this input to the execution phase, Epic allows transactions to read from and write to their versions directly. Notice that allocation is performed before the transaction execution, and during execution, no version search is required. Now the key challenge becomes how to efficiently determine the version numbers during the initialization phase. Let's consider one example of read-write operations on one record. Here on record 1, there are 4 transactions performing reads and writes. The writes are shown in red and reads are shown in blue. So like all multi-version systems, we create a new version for the writes. So here, transaction 1 and 3 each creates a version. And the version number for a read or write operation is the number of writes that happens before it. For example, for transaction 1, it's the first write in the batch, so it writes to the version 1. And for transaction 2, since it's the first, since there's only one write before it, it's going to read from the first version of the record. Similar for transaction 3 and 4. As you can notice, that determining this number for each operation is inherently sequential for each record. And our solution is that we determine the version numbers sequentially, but do it very fast. By this, we mean we map the initialization operations to parallelizable primitives on the GPU. Here we show an example of Epic's initialization phase. The input to the initialization phase includes the transactions. Here we're showing T1 to T4, and the read-write set of each operation, of each transaction. And here they are accessing 3 records, R1 to R3. For example, transaction 1 reads from row 1 and writes to row 2 and reads from row 3. We store the read-write set of transactions in a continuous array. And the first step we perform is we do a parallel sort of the read-write set based on the transactions, based on the record ID and the transaction ID of the read-write set. Notice that after the sort, the operations are grouped by the record that they operate on. For example, the 3 operations of transaction 1 are scattered to the 3 groups of R1, R2, and R3. Next, we perform a parallelized prefix sum of writes segmented by record ID. This gives us the version numbers of each operation. Here, for example, for row 1, since there are 2 writes, T2 and T4, the version numbers increment in the corresponding output. Next, we allocate versions based on the version number. Now we use the arrows in blue and red to represent the read and write access to the versions. Here, for example, in row 1, the first read happens before the first write to the row. Therefore, it should read from the previous epoch. That's why we note that V0 of R1 is from epoch 0. And then there are 2 writes, T2 and T4, to the record 1, and we create 2 versions in this epoch, V1 and V2. And T3 reads after T2, so it reads from the version created by T2. Next, we assign the version locations based on this information. Firstly, we pull out the versions that are from the previous epoch. We name them the prev versions. And we also find all the last version writes to each record in this epoch, because we only need to save these versions across epochs. We name them the next versions. All the remaining versions are created in the middle of the epoch, and they are only accessed by transactions in this epoch. We name them the temporary versions. And we pull out the temporary versions and store them in the scratchpad memory area. Because these versions are created in the middle of the transaction and they do not need to be stored after the epoch finishes. And the scratchpad memory area can be entirely reclaimed at the end of the epoch. The prev and next versions are stored in the database table. We actually store 2 versions per row because, as you can see here, that the operations accessing the next version can conflict with operations accessing the prev version. So we use the idea similar to double buffering to solve this issue. Now we have assigned the version locations for each operation. We scatter the version locations back to transactions. And now, as you can see, the 3 operations of transaction 1 have their assigned version locations. And we call this the execution plan of epic. During epic's execution phase, transactions can directly access versions based on the execution plan. And notice that no version search is required at this phase. And after the execution phase has finished, the entire scratchpad memory area can be discarded. This allows epic to perform fast allocation and garbage collection of temporary versions. Epic allows execution phase to run on both GPU or the CPU. For GPU execution, epic takes advantage of the more parallelism and higher memory bandwidth on the GPU. And to support larger data sets that don't fit on the GPU, epic transfers the execution plan from the GPU to the CPU to allow transaction execution to happen on the CPU. Next, we show our evaluation result. We use a cloud machine with 32 epic cores for the CPU-based databases, and we use the A6000 GPU for the evaluation. We use the TPCC and YCSB benchmarks for evaluating epic. Here, as you can see, epic is shown in red, and we also show the epic version where the execution phase is happening on the CPU in blue. And under low contention, epic is able to outperform the single version system OSDO. Under high contention, epic also outperforms the multi-version CPU system MSDO. For the CPU-based execution of epic, it performs slightly worse under low contention than the single version OSDO, but surprisingly, it is able to outperform even epic under high contention. In conclusion, epic proposes a novel design for multi-version deterministic database. And epic's design reduces version allocation, version search, and garbage collection overheads by allocating and locating versions before transaction execution. And this allows parallelizing and running these operations efficiently on the GPUs. And our evaluation has shown that epic performs well under all contention levels. And our work is open sourced on GitHub, and I'm happy to answer any questions.